So hello, welcome to the Security Dev Room. Get a seat and we'll start by introducing Kai from Germany, who is going to talk about Panopticon, IDA disassembler. Welcome.
Thank you. I'm Kai from Bochum. I'm a hacker, and I'm today here to tell about an open source project called Panopticon, which is a cross-platform Libre disassembler. So I will first talk a bit about the goals of the project, and then we will come back to reality and see how the project actually is implemented now. And if the time isn't up there yet, I will tell a bit about architecture. But first, I want to make the case for why we need such a tool. And well, when we're in security, especially, we need disassembler for analyzing proprietary software, for example, finding bugs in tools like Windows, and analyze malware, because most of the malware doesn't come with source code attached. And often, when we are just free software developers, we often want to implement free software replacement for file systems or network protocols that are implemented in proprietary tools only. So we have to rip those tools apart too. That's what we need a disassembler to. And most of the tools we use now, especially in security work, are all proprietary. So the idea about the Panopticon project is to build a replacement for these proprietary tools. And so when I'm talking about reverse engineering, I'm talking about binary reverse engineering. So we're only concerned about ELF binaries or PE binaries that are implemented in machine code. And what I'm also not talking about is automatic reverse engineering. So what we are doing here is mostly about manual reverse engineering. So Panopticon has this kitchen sink approach where you have one tool that does everything, and everything is integrated and at your fingertips. And you have an integrated graphic user interface to allow you to surf the code and figure out what the application does. So disassembly always starts with the disassembly. And this is where most of the open source tools stop. So we have our binary code. We can reverse the last assembly, the last step of the compilation of the assembly, because it's more or less a one-to-one mapping between bits and the assembly code listing. And for example, tools like ObjectDump just dump the assembly code onto the console and let's read it. But that's not something you can really use in reality, because most of these tools have millions of lines of assembly listing, and we are not interested in 99% of the code. Because if you know a bit about programming, we already know how it's implemented. What we're interested in is this little part in the application that implements the state machine for the network protocol, or that checks that file system, or that implements some kind of backdoor. So what the advanced tools do is what's called static analysis. So it takes that assembly code listing and cuts it up into chunks. So the concept of functions, for example, exists on the assembly level. So we can separate the code into functions, and then separate the functions in something called basic blocks, which are sequences of assembly code instructions that are executed without interruption. So we know when the first instruction is executed. Execution will continue until the end of the basic block, and then we have a jump or a branch. So our tools try to recover this information, build a nice graph, and then comes the last part, which is often overlooked, especially by open source tools. And I think this problem is mostly cultural. We have to get the information that's in the computer into the brain of the user. So we need a graphic user interface. So the interface part is the important one. What we essentially have to do is to transform the information in the computer in a way that our brains can well understand it. So with Panopticon, we take a step that's not often done by most open source tools, is that the graphic user interface is an integral part of the system. So when you implement a feature, or what you want me to implement a feature, you have to tell me not only how it interacts with the disassembler part and the static analysis part, but also how do we represent the information we gather to the user in a way the user can actually use. So not just dumping into a text file or something like that, but turning it into pictures or something like that, that we can actually help the user to understand the binary. So that's really important. Another thing most of the even proprietary tools lack is analysis based on semantics. So what most tools do is they know how assembly code looks like. So they know this bit pattern turns into this mnemonic, and the mnemonic is a string. And we know how the arguments look like, and the arguments are also strings. And that's pretty much it. It just gives you the dead code for you to read. But what's more interesting is when we have a tool that actually understands the semantics of the code at runtime. So what Panopticon does, it implements an intermediate language, it's a bit like you use in compilers. So for every mnemonic, we recognize we also generate a short sequence of intermediate language that's easy to analyze that implements the semantics of this opcode at runtime. And when we have the semantics, we can do analysis on the semantics instead of just at the syntax of what it looks like. And I will give you 2 examples what we could do when we have the semantics. And the first one is called abstract interpretation. The basic idea here is that we have an analysis across all possible paths throughout the program. And instead of just looking at one path and one value at a time, we just replace concrete values with sets of values or abstractions of sets of values. So what I mean with that is here a bit explained. So we have the C code on the left, and that implements a switch statement. It's just a bunch of cases, and when you have a certain set of cases for value, we print prime, and if it isn't, of course, this is all primes, and if there isn't a case, so we return false. And what GCC does from this code is it implements something resembling a binary search tree. So if you first start with the middle case, which is 11, I think, and we'll look if value is equal to 11, and if it's equal, of course, it jumps to the basic block that implements the print. And if it doesn't, it compares whenever value is larger or smaller than 11, and then branches according to that. And so you have some kind of tree that unfolds towards the bottom. And at the bottom, you have the false case where everything flows together. So what we often are interested in is, OK, what are the values that causes the printf to fire? And of course, when we are an experienced reverse engineer, we can always see that this is a binary search tree, and this is probably a switch case statement. So we read the code and check for all the equal, for the comparisons and the equal jumps. And then we see that all the equal jumps flow into one basic block. What abstract interpretation can do is automate exactly that. So it can execute the code, figure out, OK, when this jump is taken, value must be 11. And this jump is taken, value must be 19. And it can take the superset of all the possible values and show us that. There are limits to that, of course. Doing abstract interpretation, of course, across the whole program is hard, especially when you have things like I/O. But again, you can do this manually. But having a machine to do it for you and presenting it to you helps you to concentrate on the big picture and do that what the machine can analyze, which is inferring what this means, so what it means when val is 11, for example. So just giving hints to the user will, I believe, make reverse engineering way more easier. Another thing is called bounded model checking. As opposed to abstract interpretation, with bounded model checking, we only care about one specific path throughout the program that is feasible under a set of constraints. So one example where we could use this is, OK, this code is a bit artificial, but it implements some kind of sanity check on a network protocol or a file system format. So we have 2 inputs, A and B, that's just answer integers. And we first check that A is smaller than B, and then A mustn't be 0. And then we multiply A by 3 and invert B. And then we add them both together, and we expect this to be hexadecimal 42. So when we are compiling this, we get something that looks like we have on the right. So we have all the checks. And the true branches are the fall through here. So we want to follow the red lines. And the last basic block is the one we're interested in that, again, prints the OK. So, of course, we're interested. So what does the input have to look like in order to that printf being executed? And, of course, what we do as experienced reverse engineers is we execute the code backwards in our mind. Because we check the first condition. So, OK, the addition has to be OX42. And then we trace the code backwards. And what we do in reality is we write a short Python program that just enumerates our cases until we find one. So at least that's what I do. What bounded model checking can do is generate more or less a formula from that. We add a bunch of constraints, and then we throw it into the magic binary model checking algorithm, and it will give us a possible trace throughout the program that will hit that basic block. So what we do here is we add the constraint that that last jump is taken, which just means that the 0 flag has to be 1. And then the model checking algorithm will look for a possible set of values that will fulfill this constraint and give us the values and including the traces up there. So we see on the top there, we need A to be OX15114AA6 and B something else. And what's very nice about this is that you can add additional constraints. So maybe you can see A, but maybe there are some checks before that. You already saw that check that A isn't this value, so you can add another constraint that, okay, we want that job to be taken, but as we don't want that A to be that value, we can start the algorithm again, and it will find another solution, or will tell us that there's no solution, or it will try to compute forever, and it will crash. But these are the three possibilities. So just as a reminder, the difference between abstract interpretation and bounded model checking is with abstract interpretation, we are looking at all paths at the same time, and with bounded model checking, we're just looking at one path. So aside from that, some other features I would like to see, and ascending order of outrageousness. What would be really nice, so Panopticon is meant as a static analysis tool, but having dynamic information is always very helpful when you have huge applications. So, of course, with the semantic information, you could simulate the whole program, but this is very expensive, and especially with bounded model checking, you can't do this on real-life applications. So it's pretty much impossible to do bounded model checking on a whole Chromium instance, for example. So having the ability to include traces from PIN, for example, dynamic RIO or just the GDB instance would be really helpful. And what I would like to see is that we can match the traces onto the control flow graphs, and that can tell us, okay, when we have this input under this environment, control flow flows like that, and when I change that value or that part of the environment, control flow flows like that. So that would be really helpful, I think. And the nice thing is we already have the traces, we already have PIN, we have dynamic RIO. We just have to implement the matching and the reading of these traces. Of course, you always need scripting support. When you have a powerful tool, you want to automate things. So embedding any type of scripting language would really be helpful. I would prefer to have only one. And I would like I don't want to start doing any language war, so, but we can do pretty much everything Ruby, Python, Rails. I'm not a fan of Lisp, so in case you want to guile, that may be a longer discussion, but I can live with everything. And well, when you want to replace IDA Pro, you have to replace Hexrace, so a decompiler would be pretty nice. Even a decompiler doesn't really decompile, so the C code you get out there isn't really C code that was written, especially when the program wasn't written in C. And but you only get that code. So this kind of bounded model checking can be done on C, but there's no real use in doing it in C instead of in the assembly code. But the control flow structures you have in C are easier to read. Your control flow graph is always planar. You have high-level type information. It makes it easier to read real-life applications. So having some kind of decompiler would be nice. This isn't as impossible as it looks like, especially when you have semantic informations. You can use abstract interpretations, for example, to recover stack layouts and the use of stack frames throughout the program. And then you only have to do a type inference algorithm. So back to reality. This is all nice, and part of this is implemented, especially the abstract interpretation part. But aside from that, the program isn't as far as I wanted to. So how does it look like? A bit like that. So we have a graphic user interface. It's in Qt. You can open the application. You can open the file. And then we'll start disassembly at the entry point, and we give you the list of functions. You can click the list of functions. You get a control flow graph. You can pan around, can zoom, can click on one of the lines, add comments, save the whole thing. That's pretty much it. We can disassemble Intel architectures, as well as two of the smaller 8-bit microcontrollers. We have semantic information for the 8-bit microcontrollers pretty much complete. And well, Intel is another thing. We have more than 500 mnemonics in Intel, and so you have to write the semantic information for 500 or so opcodes. But this isn't as bleak as it looks like, because when you look at real-life applications, when you implement around 100, 120 of the most popular opcodes, you already have 99% of everything that's in there. And as I said before, we are not really concerned about global program analysis. We just want a local reasoning about that function or that set of basic blocks. So what happens at runtime? How do I get to the path there? So it isn't as important that we have 100% that we are 100% precise. We're not trying to do symbolic execution or do automatic exploit generation. We can open ELF files. I actually have a pull request open pretty much now. I will merge when I come home and get a bit of sleep. So we will support PE files too. And aside from that, we can roll the raw flash dumps for AVR, which isn't that complicated. Also, the project is hosted on GitHub. We have an open development model. We use the issue tracker there. So in case you have a question, you can open an issue. I will try to answer it. And if you have a patch, you can send it as a pull request. So I have a bit of time left, so I will talk a bit about the architecture. The application is in one repository, but it's two parts. So we have one library that does all the disassembly, the static analysis, and the representation of the code. And it's written in Rust. In case you never used Rust, it's not that much different from C++, for example. So I started Rust 1.5 years ago, and it took me 3 months or so to understand it in a way that I can program tools like that. So it isn't that complicated. We also have the graphical front end, which is a bit Rust to interact with the library. And on top of that, it's QML. That's some kind of JavaScript derivative that's used by Qt to implement widgets. So when you clone the repository, you see something like that. The library consists of around 20 files that are more or less named after the thing they do. We have the abstract interpret, which is the abstract interpreter. And then we have the assemblers for AMD64, AVR, and MOS. And then we have some kind of tree of the representation of the program. So at the lowest level, we have the mnemonics, which is mnemonic RS. Mnemonics are grouped into basic blocks. Basic blocks are grouped into functions. Functions are grouped into programs. And programs are grouped into a project. And the project is sort of the top-level node of what's saved in the application. And well, you have the data definitions in there. You also have ILRS, which is the definition of the intermediate language we use there. In case you're more on the academic side, we use Rail. But it's a derivative of Rail, and we have some custom functions, custom operations in there. And well, the front end isn't that complicated. We have a bunch of Rust files to communicate with the library and do the layouting for the control flow graphs. And aside from that, we have a folder called QML, where all the QML files live. Each file implements one widget. That isn't that complicated, so in case you never use JavaScript, it isn't that JavaScript-y as you would expect. Also, Qt has a really nice documentation, so you can check that out. It's pretty straightforward. So, in case you're interested and may want to help me and or just want to check out the project, we have a website. We have on the website there the link to the API documentation, the users documentation, and you can also jump to the GitHub repository directly. And also, if you have a question, you can reach us on the Freenode channel. And also, we have a Twitter account where we mostly post about news about the project. So that's it.
Thank you, Kai. So we have 5 minutes for questions. We have the first one here.
Wondering why Rust? I mean, I love Rust, but I'm wondering why.
The project started years ago, and I used C++ because why not? And I'm sick of C++. And when I saw Rust solves the problems I have with real-life C++ applications. And this is my hobby project. So I just thought to myself, why not use Rust? So 1 year ago, I just rewrote the application that was at that time 10,000 lines of code into Rust. And turns out it was way easier than I thought. I actually got the line count down to 8,000. I have less bugs. And Rust really helps me to avoid the kind of bugs you have with C++ code bases, like iterator invalidation, data races. It's way less painful to program Rust than C++.
I was wondering about obfuscated malware, and in particular, there are some TTPs that you can recognize so easily that you could potentially build semantic information for that.
Yes. Of course, obfuscation is there to stop us. There's only so much you can do. That's why it's interesting to have dynamic information. So when you have something that unpacks itself at runtime, you can do a snapshot and import it. Also, when you have things like virtualized malware, where you have some interpreter in there, what you can do is use the scripting engine to implement some kind of lifter for that intermediate language after you have disassembled it, and then use, because you only have to generate the intermediate language, and then use all the code analysis features that are built in there to do code analysis directly on the obfuscated virtualized malware. But of course, this is a problem. It's there to stop us. We can all do so much.
Follow-on question on that. Do you have disassembler for other language? You had C, but were you thinking to disassemblers to C++ or some other high-level language? Or are you planning it?
You can decompile to C++ too, right? Also with C++, you have the advantage that you can try to pattern match certain parts of the C++ compiler to figure out how, for example, class hierarchies look like.
But right now it's C.
But only for now you can analyze assembly code listings. But
Okay.
of course, you can even analyze Haskell. It just looks a bit crazy. Yeah.
So we have 2 more questions planned. Raise your hand if you want to ask more.
It's a simple question, but what's the logic behind the decompiling? It's besides of the scope of this the talk, but when you decompile a list of the assembly, you decompile in C or C-like. What's the logic behind you pick a code of C associated by a list of assembly besides another?
So what you can do is what, for example, IDA Pro mostly does is pattern matching. You can, of course, the compiler turn certain constructs into certain assembly code listings, and you try to recognize that and turn it back. And other ways is to just turn the code into C. So you turn it into some kind of C expressions, and then you can turn the assembly code expressions into a C expression. The decompilation is just 3 processes. You only have to recover the control flow architecture, the control flow constructions in C. So you can do this with pattern matching. You see, okay, when I have a block that just have a loop, okay, that's loop. So you can turn it into loop. What's more complicated is to recover the type information and then to recover how the stack is used. That can be done with assembly with the abstract interpretation. And the type information, where you can do a type inference algorithm, you have with Haskell or with Rust. And for this to work, you also need typing information. So you need to encode into the disassembler that certain API calls have a certain type set. So you can use this when the assembly code calls the function. You know, okay, the arguments must have test types, and you can try to push the information down into the assembly code. So that's pretty much how decompilation works.
Okay, thank you.
More questions?
One question. Actually, there are 2. First question: what was the reason not to use any of the existing disassembly libraries, which would give you access to more processor families? And the second question would be: is there an option for example, another type of syntax like AT&T syntax? I noticed you use Intel syntax for the x86.
So currently, we only let's start with the assembly question. The problem is that the assembly libraries you have now don't give you really semantic information. There's capstone, which can tell you at least which part with arguments are written and which are read, but it can't tell you what's the function between those 2 arguments. And doing this is the most of the work. So I saw no much use in trying to wrap library, because trying to wrap C libraries and having it compile flawlessly on most machines is very hard with Rust. So when you only have Rust, it's easier. And okay, of course we can generate AT&T syntax. We can put a switch in there. Currently we have Intel hard-coded, but that's not much of a problem. My time's up.
Okay, let's thank Kai. And there's a 5-minute break. Please open the door so we can get some air in. Thank you.
I need to tell you one thing, both of you. So you are responsible of these rumors?
Yes, I guess so.
Because I'm a journalist from Italy.